Let's look at the Banach-Tarski paradox. So this builds on the idea of a non-measurable set, as we saw in section 2.6 of Royden and Fitzpatrick. The title of the presentation is Non-Measurable Sets and the Banach-Tarski Paradox. Much of this material is based on a book called The Pea and the Sun, a Mathematical Paradox by Leonard Wapner. The reason for the title is the Banach-Tarski paradox will imply that we can take a sphere of a certain volume, partition it into some pieces, glue those pieces together, and create two spheres. So we create twice the volume out of nothing, apparently. So that's the sense in which the word paradox is being used. It's not a paradox. It's not a mathematical paradox. In light of what we've recently done, it's what you get when you deal with non-measurable sets. We'll deal with non-measurable sets in 3D, largely in this write-up. We'll look at the non-measurable set P that we constructed in section 2.6 of the third edition of Royden as well. But paradox, it's shocking, the result we'll get. But it's simply some of the strange things that happen as a consequence of the axiom of choice and as a consequence of the implication from the axiom of choice that non-measurable sets exist. It's simply some weirdness we can do given that we don't have countable additivity, or maybe even finite additivity, when we deal with non-measurable sets. So that's all. It's worded in some kind of a physically intuitive ways that make it particularly paradoxical, particularly, logically obnoxious. It's just a weird implication from the axiom of choice. Now, George Cantor is the chap who defines an infinite set and deals with cardinalities of sets and what it means for two sets to have the same cardinality. He defines an infinite set as one for which there's a one-to-one mapping from the set to a proper subset. For example, the natural numbers form an infinite set. To verify Cantor's definition, consider the mapping that takes x to x plus 1. That maps the natural numbers to the natural numbers except for 1. So it's a one-to-one mapping from the natural numbers to a proper subset of the natural numbers. And so by Cantor's definition, this is an infinite set. We could kind of visualize this mapping as 1 is mapped to 2, 2 is mapped to 3, and so forth. And 1 isn't the image of anything. Such a mapping is called a shifting to infinity. Think of it as a rigid mapping, that is, distances are preserved. A lot of what we're about to talk about is distance preserving mappings. They're called isometries, mappings that preserve distances. So what we've done under this particular mapping is we've sent the natural numbers to the natural numbers set minus 1, said that 1 is shifted to infinity, and it's lost in this rigid transformation. So by doing this, we've lost 1 in the image of this one-to-one mapping. Kind of related to this, there's a story of the Hilbert Hotel, it's called. Possibly you've heard of this before. It's a common sort of popular story on the weirdness of infinity. Story involves a hotel with a countably infinite number of rooms. Suppose every room is occupied and somebody new shows up and they want a room. No problem. All you got to do is make every person move one room over. Take the person in room I and move them to room I plus 1, like the mapping upstairs. That frees up the first room and you can put this new person in. So at the Hilbert Hotel, there's always room for one more. In fact, there's always room for countably many more. If a countably infinite number of people showed up, we could move the person in room I to room 2I. And that would free up all the odd numbered rooms. And you could put the new countably infinite number of people then in the odd number of rooms. That's just some weirdness from the fact of having dealing with sets that are infinite, actually. All right, we're going to look at sort of similar type transformations, but this time with the unit circle. In R2, we'll ultimately look at the unit sphere in R3. But for now, consider the unit circle in R2. That is, all points x, y, such that x squared plus y squared equals 1. We're going to create a set N by taking the point 1, 0, so the rightmost point on that circle, and the point 1 unit of arc length away, say in the counterclockwise direction, the point 2 units of arc length away, and so forth. So we're moving around the circle in unit arc lengths and picking points off of the circle. That's how we're doing this. So the circumference of the circle's irrational. It's 2 pi times the radius. The radius is 1, so it's 2 pi. Since that's irrational, then as we pick these points off, we never repeat points. So creating a set N by so choosing points on the unit circle does indeed create an infinite set. We did it by moving 1 arc length, 2 arc lengths, and 3 arc lengths, and so forth. So it's a countable set also. So set N is a countably infinite set. Let's take this circle, unit circle C, decompose it into set N, the points we just picked off of the circle, union the rest of the stuff, the rest of the circle, C set minus capital N. Now, we can rigidly rotate this set N through 1 radian. Just as we did above, we're just shifting everything by 1 unit. This time we're going around a circle instead of along a straight line like we did with the natural numbers in the picture we initially saw. This maps the nth point of set N to the n plus first point of N. It leaves the C minus N, the points on the circle not in set N, it leaves those fixed. So we have a 1-to-1 mapping. By the way, it's not onto because it's missed that first point. It's missed the point 1, 0. So we've taken C, broken it into 2 disjoint pieces, rigidly rearranged the pieces. We simply rotated through 1 radian, that's set N, and we've produced a copy of C that's missing 1 point. So it's a cute little trick to take the idea about the natural numbers, apply it to countable sets in this case, and create a 1-to-1 mapping, not an onto mapping, but a 1-to-1 mapping that misses a point. It misses that point 1, 0. Again, that point is said to be shifted to infinity through this rigid rearrangement of that set. So the idea is exactly this. We've taken set C, we've removed a point over here and gone 1 radian over, a 2nd radian over, a 3rd radian over, and bounced around removing those points. What we're left with here is a smattering of points. Kind of reminds me of the rational number. I bet you between any 2 points along this circle, there's another point along that circle. It's a countable collection. We know it's a countable collection for sure, given the way we chose it. It's infinite as well, based on the irrationality of the circumference of the circle. And this is what's left. And I would think, well, this kind of has the distribution then of the irrational numbers, except it's around a circle. Between any 2, there's another one, and there's uncountably many in this distribution. So the complement of what we have up here. We rotate this one around through 1 radian, mapping the first point to the second point, and so forth, and leave this fixed, glue them back together, and that rightmost point has been shifted to infinity is the verbiage they use. But we've got a 1-to-1 mapping. We've shifted a point to infinity. We could shift any finite number of points to infinity in a similar way. We could map the first point of set N, the rightmost point. We could map it to the 3rd point in set N, the way we picked them out, a 1st and a 2nd and a 3rd. And then that would omit the 1st and the 2nd points in the image, and we have 2 points missing here. we could do more sophisticated mappings, maybe not more sophisticated rigid mappings, but it would be possible also in a one-to-one style to map, to every other point, like we did when we let an infinite number of people into the Hilbert Hotel. So there's other ways to do it. You might argue that's not a rigid transformation, though. And we're wanting to preserve some rigidity in what we do, because we're going to want to preserve links and areas and volumes, ultimately, in the Banach-Tarski paradox. We could fill these circles in and treat them as disks. Maybe have a unit disk and introduce little line segments. So for each point on the circle, go to the center of the circle and connect it to those points with line segments. And we could have actually have mapped a line segment, a radius of this circle mapped to infinity, and we could lose that if we treated these as disks instead of circles. Okay, now I call it a magic trick. It's highly unintuitive what's about to happen. You need the background from section 2.6 from Royden's book. You need the idea of the construction of that set, capital P, we called it, the set that we constructed as a subset of the intervals 0, 1, excluding 1, including 0. We had taken the axiom of choice, used rational equivalence, axiom of choice applied to those equivalence classes, and produced a set P, which we showed to be not measurable. We did so by taking that set P and translating it by rational numbers, creating a countable collection of sets, which partitioned up the interval 0, 1, and all these sets were the same size. They were the same outer measure because they were translates. Well, translates mod 1. Circle plus translates was a notation we used in section 2.6 of the third edition. The fourth edition does things slightly differently. I like this. This works well and fits better in our conversation about Banach-Tarski. But we did the circle plus translation stuff. And these P sub i's disjoint, pairwise disjoint, they partition the interval 0, 1 up into a countably infinite number of pieces. And they were all the same outer measure. If you like, they're all the same size. And that led to some problems. And that's how we showed that set P is non-measurable. Okay. We saw as well in that presentation, so as I said, it depends heavily on the development in section 2.6. We could take any one of the P sub i's and translate it to any of the P sub j's by circle plus adding the appropriate rational number. Let's denote that rational number as Q sub ij. And P sub I and P sub j were both circle plus translates of the original set P. So I can, with a rational number, translate any P sub I into any P sub j by adding the appropriate rational number. Okay, we had that the interval 0, 1 was a union, actually disjoint union, of these P sub i's because they formed a partitioning of that. Okay, we got a countable collection of sets, and we can take one and translate it into the other by circle plus adding the appropriate rational number. So we're going to do the same kind of thing we did above when we had an infinite number of new people show up at the Hilbert Hotel. So here's the plan. We're going to take these P sub i's and create two copies of the interval 0, 1. We'll take P sub 1, circle plus 0. So P sub 1's mapped to P sub 1. Let's take P sub 2 and map it to P sub 1 as well. That can be done by adding the appropriate rational number. The notation I've introduced is Q sub 2, 1. It maps P sub 2 to P sub 1. Such a mapping exists. Take P sub 3 to P sub 2 by adding the appropriate rational number, P sub 4 to P sub 2. So what we're doing is we're taking all the odd indexed copies of P's and mapping them to P1, P2, P sub n, and so forth, mapping them to all the P's, and we're taking all the even indexed ones and mapping those to all of the P's as well. So we've got a mapping that takes this countably infinite copy of p sub 2's to two countably infinite copies of the p sub 2's. Well, if I'll glue all these together, we'll get the interval 0, 1. And if I glue all these together, we'll get the interval 0, 1. So what we've done is partitioned up the interval 0, 1, including 0 and excluding 1, into an infinite number of pieces. And we've rigidly translated those pieces and created two copies of the interval 0, 1. So we had a total length of 1 initially, and now we've created a total length of 2. Where'd that extra length of 1 come from? I could take all these along the bottom and add 1 to each of them. That's translation as well, a rigid transformation. And we could produce the interval, say 0 to 2, if you like. No matter how you slice it, we started with a set of length 1, and we've created a set of length 2. That's why I'm interested in rigid transformations. I take these sets and I translate them. Maybe I translate, cut off a piece and translate that. That's what the circle plus stuff accomplished. But these were always rigid transformations. In so doing, we seem to have created a length of 1 out of nothing. So that's the magic trick. What's really mathematically going on here? We're violating countable additivity. Because remember, these sets P, the set P, and all these P sub i's, they're not measurable. That's why you can do this funny behavior. If they were measurable, you'd take that interval 0 to 1, cut it into a bunch of measurable pieces, move them around, add up the lengths, still going to get 1. That's countable additivity, countable number of pieces. Well, we don't have a measurable set here, and that's what's allowing us to do this weird stuff of apparently creating a length of 1 out of nothing. So that's the paradox. I read paradox as there being a logical problem, which is probably bad on my part. That's not exactly what the word means. But nothing's wrong logically. We're dealing with non-measurable sets, and funny stuff like this happens. I'd say get over it. That's what happens in measure theory. The story does get weirder, though. You can't read a physical interpretation into this pure math stuff. Okay, we could modify this mapping up here. We could iterate the process, whatever you want. We could produce as many copies of 0, 1 as you want through this process. So we could take that interval 0, 1, cut it into a countable number of pieces, and rigidly translate them around and create any interval you want. We can even create infinite intervals. We could create the whole real line if you like. So that's pretty weird. But that's because you're looking at non-measurable sets. Okay. We could maybe, I'll touch more informally here, take that interval 0, 1 and wrap it around a circle. Say a unit circle, have to stretch it a little bit. The circumference of a unit circle is 2 pi, and this only has length 1. So uniformly stretch it a little bit. But anyhow, you could wrap that around a circle and do the same kind of partitionings and actually take a disk of radius 1 and create, through rigid transformations, 2 disks of radius 1. Now, this has to be done with countable numbers of pieces. We'll make a comment later. The fact that we had to use infinitely many pieces is kind of an artifact of being in 1 dimension, or in 2 dimensions when I've given this little informal description here. What the Banach-Tarski paradox says is a solid ball may be separated into a finite, that's new, finite number of pieces and reassembled in such a way as to create 2 solid balls, each identical in shape and volume to the original. Reassembled, right, they're informally saying reassembled. More formally, they're doing this all with rigid transformations. So you can take a sphere, break it into, turns out we'll break it into 5 pieces. We can glue 2 of those pieces together and get a brand new sphere. Take the other 3 pieces, glue them together, and get a second copy of the sphere. Where did that extra volume come from? Well, you don't have countable additivity. So that's a thing that happens in measure theory. But that is the Banach-Tarski paradox, that we can take a sphere, break it into pieces rigidly. If I was only able to stretch things, nobody's surprised, but it's rigidly taking pieces, translating them, sticking them back together, and getting new spheres. The Banach-Tarski paradox does not hold in the plane. A space of 3 or more dimensions is required. Well, we did something like that, but it took us an infinite number of pieces. So this comment means, well, you can do the same thing in 1 and 2 dimensions, but it requires an infinite number of pieces. Part of the shocking bit of the story is you can do this with a finite number of pieces when you get up to 3 dimensions. And we'll mention 5 pieces as a minimum number before we're done. You might be familiar with Stefan Banach. Excuse me. Banach spaces are named after Stefan Banach. Tarsky, I'd be a little surprised if you've heard of Tarsky before. His fame, I think his fame comes from the Banach-Tarski paradox. Banach, active analyst, maybe a functional analyst. Banach spaces are commonly studied in functional analysis. Active probably in the 20s and the 30s was when the Banach space ideas came up. They sort of come hand in hand with Hilbert space ideas, and the Hilbert space stuff dates from the 20s and 30s as well. Tarsky, I really don't know much about him, but in 1924, Tarsky, I think he's more of a topologist than an analyst. But the paper introducing the Banach-Tarski paradox, those are the 2 authors, so that's how I got the name, is introduced in 1924. There's a reference for you. Their work heavily depends on earlier work of Vitali, and no surprise there, because that non-measurable set is sometimes called the Vitali set. And Hausdorff, if you've had much of an encounter with topology, you've certainly encountered Hausdorff's name before. Purely in analysis, maybe you haven't seen Hausdorff's name pop up before. Okay, so we're going to try to get through some explanation of how the Banach-Tarski construction works. The P in the Sun book, the Wapner book I mentioned earlier, gives them a moderately detailed explanation of what's going on, especially with the background of knowing how that set capital P, that non-measurable set, is constructed in the Vitali construction. But here's what's going on with Banach-Tarski in 3 dimensions. So I say the following it's a vague description. I'll make a handful of claims that I will want to justify. I don't know how to justify necessarily. I've been through the Wapner book, but nothing more technical than that on the Banach-Tarski paradox. It's parallel arguments, I'm sure, to the way we've dealt with the non-measurable set P. But we got a little more room in 3 dimensions. Okay, so first consider the 3 sphere, the sphere in 3 dimensions, I should say. X squared plus y squared plus z squared equals 1, points x, y, and z in 3 dimensions. We're going to consider 2 rotations. Here we are with x, y, z coordinates, x-axis, y-axis, and a vertical z-axis. I want 2 rotations. One of them is 180-degree rotation about the line x equals z. So x-axis, z-axis, as best I can draw in perspective, the line x equals z, line with slope 1 in the xz plane. Take a rotation of 180 degrees, let's call it sigma, about that axis. A second rotation, we'll call tau, is a 120-degree rotation about the z-axis. So rotate through 120 degrees about the z-axis. So that's our 2 rotations. And with those 2 rotations, we're going to go through and create these weird little sets that allow us to create 2 spheres out of 1. By taking combinations of these 2 rotations, sigma and tau, we can generate an infinite countable group G, which maps the sphere onto itself. In other words, take the group generated by sigma and tau. The subgroup generated by sigma and tau of the group of all symmetries of the sphere, the 2 sphere. So anyhow, it produces a group. It's countable. It's infinite. And we're going to partition G into 3 pieces, G1, G2, and G3, being pretty vague on what those pieces are exactly. And this partitioning of the sphere is done so that those 3 pieces satisfy the following conditions. It's really this last one that's accomplished some strange things. Tau of G1 equals G2. Apply tau to the first piece, get the second piece. Tau squared of G1 equals G3. So apply tau squared to G1. That produces a third piece. And sigma of G1 equals G2 union G3. All right, so that seems a little strange. These are infinite sets, and I'm not surprised I can map one infinite set to another. The rigid transformation stuff is maybe a bit surprising, but I'm going to make some kind of informal arguments here, and there's got to be some kind of flaw to these arguments. I'm going to talk about, it's kind of like this is a third of the sphere. We've taken the sphere and broken it into 3 pieces, and we can rigidly translate one piece into another. So it sounds like those pieces are the same size. Got a problem with that though down here, because this piece seems to be the same size as those 2 pieces together. And remember, this was a partitioning of the sphere. Since each element of the group is a type of rotation, then each such element of the group, each such rotation, has 2 fixed points associated with it, the poles of the rotation. We're taking a sphere and rotating it. Okay, there's going to be 2 points that are fixed under any such rotation, is what we're talking about there. Denote the collection of all such poles, that is, poles, points on the sphere associated with that group of rotations, the group generated by sigma and tau. Denote by P all such poles. The group will partition the remainder of the points, S set minus P, into an uncountable number of orbits. Okay, that's kind of what we did when we dealt with the rational equivalence. We went through and we had an uncountable it had uncountable equivalence classes, a countable number of, let's see, let me get it straight. Sorry, we had a uncountable number of equivalence classes. Let me think for a second, let me get my cardinality straight. We partitioned up the interval 0, 1, that's an uncountable set. We created the equivalence classes, and there were, there were an uncountable number of equivalence classes, and each equivalence class was countable. I think that's how the cardinalities fit together. Here, we're getting an uncountable number of orbits. We'll introduce a term, I think we use the term similar here shortly, to say 2 points in the same orbit are similar. You might talk about it in terms of a transitivity when groups are applied to objects. We do that in graph theory. But we get an uncountable number of orbits, just like we had an uncountable number of equivalence classes when we did our set P stuff. As with a set P, we're going to use the axiom of choice to choose a representative of each of these orbits and call the resulting set C. Okay, so very Vitali-esque in that we've used the axiom of choice. We've chosen representatives, this time from orbits, back in the Reuten book from equivalence classes. It's the same idea. And we've created a set C. Sometimes it's called a choice set. Set C is similar to the Vitali set that we created from the interval 0, 1. Similar, not a mathematical term, they're created in analogous ways. Now we're going to apply all the permutations from the 3 pieces of G to create a partitioning of the sphere. Okay. Apply the rotations of G sub I to this set C that we've created to create sets K sub I for I equals 1, 2, and 3. Okay. That gives us a partitioning of the sphere into 4 pieces. The K1 image of C, the K2 image of C, and the K3 image of C. Remember we threw out all those poles, so we've still got those points left over. Those poles were what? Associated with elements of the group. Okay. The group had countably many elements. So the number of poles is a countable set as well. So we got a countable set here. These other ones, not countable. Okay. Now, we know how the G sub i's, the G1, G2, G3 things, how those are produced. So we get similar relationships between these K's. We've got, up here we had tau of G1 equals G2. Down here we'll have tau of K1 equals K2. Tau squared of G1 equals G3. Tau squared of K1 equals K3. And similarly, sigma applied to K1 will be the union. Okay. So we see K1 can be rigidly rotated to produce K2, use the tau transformation. K1 can be rigidly rotated, tau squared, to produce K3. And K1 can be rigidly rotated using sigma to produce K2 union K3. When one set can be rigidly rotated to give another, we say the sets are congruent. So here's the verbiage we'll use. So what we have then is K1 is congruent to K2, is congruent to K3, is congruent to K2 union K3. This is called the Hausdorff Paradox, and here's what's paradoxical about that. We've broken the sphere into 3 pieces that are congruent. They've got, they got the same shape when I can rotate one into the other. Well, this is, I want to say, this is basically the whole sphere. That's misleading. We threw that set P out. That was just a little countable set. But anyhow, we've taken this sphere and we've broken it into 3 pieces, K1, K2, and K3, and they have the same shape. One set can be rotated into the other. So I feel, this ain't math, like each of those pieces is like a third of the sphere. Well, except we threw away the set P. But that was a small set. It was a little countable set. Countably infinite, but still a countable set. So it seems like K1, K2, and K3 should have a volume of about a third of the volume of the sphere. Yet here we've got K1, K2, and K3, similar, what was the word, congruent, and also congruent to K2 union K3. Now remember, those are disjoint. This should be 2/3 of the sphere, it seems. So this is what they're calling the Hausdorff Paradox. Yeah, so we've got some really weird behavior. Remember what lies under all this? Non-measurable sets. And so we get some weirdness in the way they behave. When we union the 2 pieces, K2 and K3, we'd expect to get 2/3 of the sphere. Instead, we get something that's congruent to 1/3 of the sphere. So pretty weird stuff. Hausdorff presents these ideas, I guess, in 1914. Vitali creates a non-measurable set, and I think it was 1905. A lot of activity going on at this era. Lebesgue himself introduces Lebesgue measure in 1902. So we're looking at the first decade or 2 of the 20th century when this stuff's happening. All right, here's a real trick. We're going to start gluing these things back together. We use K2 union K3 as a cutting template. So we got a collection of sets. We're going to move this around and cut some pieces out. We place K2 union K3 on K1. They're congruent, so you can rotate K2 union K3 around to get K1. In fact, sigma inverse would do that. Take sigma inverse of K2 union K3, and that'll produce K1. So that's what they mean by place on, is use a rotation to map the K2 union K3 to the K1. And then we can cut K1 into two pieces. One piece is congruent to K2, and one piece is congruent to K3. It's the K2 union K3 part that's the weird part, being congruent to the others. Do the same to K2 and K3 themselves. All right, we can map K2 union K3 rigidly onto K2 and onto K3. We can use the little formulas up here to figure out how. Right, we could map this to K1. You want to map K2 union K3 to K3 itself. Take a sigma inverse, that'll map you to K1, and then apply a tau squared, and that'll give you out a K3. And these are onto transformations. Okay, then we'll take K2 and K3 themselves and cut them into pieces also. So we've taken K1, K2, and K3 and broke each of them into two pieces, giving us a total of 6 pieces. Now, 3 of those pieces could be put together to make a sphere. Now we got 6 pieces. Yeah, we'll make 2 spheres. A few details left to iron out about set P. Remember countable set P? So I owe you details on that. But we've got 3 copies of K2, 3 copies of K3. Well, altogether, we got 3 copies. We created 2 new copies by the partitioning. We're going to take one K2, rotate it around to give a K1. There's a transformation that did that. One K3 that can be rotated around to give another copy of K1. So through partitions and rotations, we've produced 2 copies of K1, 2 copies of K2, and 2 copies of K3. There we go. So we got 2 copies of everything. I guess I was off by maybe a layer of rotations in that originally. But gives us a total of 2 copies of everything. We can union. You might not like these little set notation I've used here. It bugs me a little bit. 2 copies of K1, union 2 copies of K2, union 2 copies of K3. You don't really have multiple repetitions of elements of a set. So this is a bit abusive of the notation, but give me a little break on that. And we've unioned that with set P. And set P, we still need, we need a second copy of set P to complete this. So we can produce 1 copy of S as S equals K1, union K2, union K3, union P. So there's 1 S. Next, we union the second 3 copies, K1, K2, K3, not to get all of S, but S set minus P. So we're still missing that. But we can shift to infinity and plug up those holes that are left by the countably infinite set P. So shifting to infinity, similar to what we did above. And we can build 2 spheres from 1 sphere. So we started with a single sphere of radius 1 with this weird partitioning up using that group action on the sphere. We're able to cut it into pieces and produce 2 spheres from 1. We had a total of how many pieces? We had 6 big pieces when we did the partitioning and the cutting up and so forth. Plus we had the P and we kind of doubled it up. So arguably we had as many as 8 pieces here. The above argument dealt with, actually technically dealt with the surface of the sphere in the conversations we had. We could easily extend that to a solid sphere by extending radii from the center of the sphere out to the sphere and including those line segments. and followed the same construction. I guess technically I did the surface in the description there, but that extends to the sphere. Okay. And here's the reason for the title of the book. We could start with a sphere the size of a pea, decompose it as described, and create 2 peas out of 1. Create that extra volume. And you could keep iterating this process until you produced a sphere of the volume of the sun. So that's the reason the book is called The Pea in the Sun. And apparently the Banach-Tarski paradox is sometimes called the pea in the sun paradox. I got to admit, till I ran across this book, that I've never heard of, but I've heard of the Banach-Tarski paradox in the past. I like to see things and what they look like. You got a problem because you use the axiom of choice in all this stuff. And that's how we created set P. We've used it here in the creation of a set as well. That means I don't know what's in it. That's a problem with the axiom of choice. It guarantees the existence of a set, but it doesn't tell you how to build that set. It's not constructive in the traditional sense. The axiom of choice guarantees the existence of a set, but gives you no clue how to construct the set. So I don't know what to visualize. I know this. Those pieces are really weirdly shaped, because if they wouldn't, we wouldn't get this bizarre behavior of making 2 spheres out of a single sphere. If we had nicely shaped pieces, we'd have additivity and this weird stuff wouldn't happen. So we must have pieces that are really weirdly shaped. I imagine these pieces look something like this. All right, so here's a sphere. And we've got blue spaces, we got green spaces, we got yellow spaces, we've got red spaces. Man, I need another color there. I'm a little colorblind, so I probably don't see all the colors that are there. But look how all mixed up they are. So I imagine something like that as representing these pieces into which we partition the sphere. This, by the way, is totally not related to what we did. This image is of the cosmic microwave background, the microwave radiation projected onto the sphere of the sky. The different colors represent different temperatures. So this is not relevant really to what we're talking about, but I like the picture as something to visualize and thinking about what the pieces look like. I'd kind of expect to see the same amount of red and the same amount of blue and the same amount of green. And this picture doesn't reflect that. So there's some shortcomings to this image. And there is no such thing as a picture of these pieces because it's the axiom of choice that's been used to create these. They're not well defined enough to actually draw pictures of them. But I think of something really messed up like this. So you might think of the sets as the colors, say. It's all mixed together, maybe like the rationals and the irrationals are in the real numbers. I don't really know how to draw a neat picture of the rationals and the irrationals as far as that goes. Well, they have similar distributions, yeah, but there's a lot more irrationals than there are rationals. So how to draw that, I don't know. Math is about ideas and not about pictures. Final comment, the construction presented here isn't the easiest in terms of the number of pieces. In 1947, so some couple decades later, 3 decades later, so R.M. Robinson showed that the construction could be accomplished using only 5 pieces and could not be accomplished using fewer pieces. 2 of the pieces form 1 sphere and the other 3 form a second sphere. There's a reference on that. So this can be done with as few as 5 pieces and no fewer. Can't be done in 1 or 2 dimensions. So it really hits weirdness in the 3rd dimension. We can take a sphere, partition it into 5 pieces, glue 2 of those pieces together to get a sphere that's got the same volume as the original. Take the other 3 pieces, glue those together, and get a second sphere with the same volume. So we've doubled the volume. Where did that free volume come from? We don't have additivity. these pieces are weirdly shaped, and there isn't additivity. So we get this odd behavior where we can partition things up and create pieces that have a volume that's greater than the volume of the original piece. Thing is, the pieces themselves, the 5 pieces, they're the weird things. They're the non-measurable things. A sphere is measurable. We've taken a sphere, broke it into 5 non-measurable pieces. So the 5 pieces doesn't even really make sense to talk about the volume of the pieces. But when I glue them together, they can be glued together nice and cleanly to make a new measurable piece, a new sphere, 2 new spheres, in fact. Don't read anything physical into this. We use the axiom of choice. It's not creating volume out of nothing. It's simply an amusing artifact of dealing with non-measurable sets. Hey, measure isn't finitely additive or countably additive in general. Outer measure isn't. That's why we stay away from those non-measurable sets, and we concentrate so much in the analysis stuff on measurable sets. So there's a little story about the Banach-Tarski paradox. Odd stuff. Again, it's just an artifact of not having all sets measurable. You don't have additivity, so you can do weird things like this. Have a nice day. We'll get back into the book now. And I think next on the agenda is talking about how many non-measurable sets there are and how many measurable sets there are. I'll see you back in Royden Fitzpatrick soon. Have a nice day.